Good afternoon, everyone. So now we'll resume our session that will be taken by Professor Arnab Ghosh, NIT Rourkela. He is going to deliver on intelligent power management scheme for microgrid applications. Professor Ghosh received the BTech and MTech degrees from West Bengal University of Technology, Kolkata, India in 2010 and 12 respectively, and the PhD degree from National Institute of Technology, Durgapur in India in 2017, all in electrical engineering. He is currently an assistant professor in the Department of Electrical Engineering, National Institute of Technology, Rourkela. His research interests include the design of power electronics converters, renewable energy sources, microgrid and smart grids, electric vehicles and vehicle-to-grid applications, etc. So you may proceed now. Sir, can you please unmute yourself? Sir, your voice is not audible.
Yes, ma'am.
Hello, sir.
Am I audible?
Yes, sir. Yes, sir.
Is my slide is visible?
Yes, sir.
Okay, I'm making it full screen. Please let me know. I hope the slide is full screen.
No, sir.
That's right. Is it full screen now?
Yes, sir. Yes, sir. Yes, sir.
Okay, okay. So very good afternoon, all the esteemed participants and that respected professors. I am Arnab Ghosh, going to deliver my presentations on intelligent power management scheme for microgrid application. Okay, so before starting the session, so first we need to about the what is the motivations for this, what is the motivations for choosing this topic. So first we need to know about that what is the meaning of that power management scheme and what is the importance for the microgrid applications and why we are thinking about it, it should be quite intelligent for our current scenario. Okay, so first when we are starting with that microgrids or power management, basically we can think about different sources for our current renewable applications in our utility grid or in our domestic grids. Okay, so especially for the scarcity of the fossil fuels. Okay, so now all kind of research and dimensions of the work is switched to that different renewable sources and their integrations with our conventional grid. Okay, so suppose we are having different sources based on the area specific, or you can say like that based on that look availability of the basic locality. Okay, so what are the different types of source we can able to say like that? There may be the PV means solar photovoltaic. Okay, so solar photovoltaic is only well known source of renewables. Okay, otherwise you can able to use wind system. Okay, Sometimes in our cases we can able to use some of the biomass gasifier or pico hydel. Okay, so all are the different type of sources, renewable sources we can able to use for our domestic applications. But problem is that all the time all the sources are not available. Okay, so how optimally we are able to how optimally we are able to manage them. Okay, means which how we are selecting the sources based on the demand of the system. And some of the sources are maybe suppose solar photovoltaic. If we see their profile, so throughout the year its generation is quite steady generations. But some other sources are there but their generations may be steady, but for that you need to feed continuous fuel on that. Okay, so that's why it is not efficient for giving the steady generations. If you are sending some fuel, suppose biomass gasifier. Okay, so for that, what you need to do, you have to feed some fixed fuel for that gasifier. Okay, so that may be the some problem. Okay, so it can be work only for the high demand conditions. Okay, that's why the but evening time, if you are able to see that time solar is not there. So how all the sources will be managed, as well as some storage you need to connect with the system that can provide you more reliability of the system. Okay, that's why the power management is quite important for our current scenario. And microgrid is very well known topic for all of us. Previously we have designed the system, means we have installed the power plant in the nearby to the base load. But now again the concept has changed, so mostly we are giving more trust on the different distributed generations, as well as you can say like the different captive generations, means you can able to generate the energy from your local areas. Okay, in that case what happens, you have to establish some regional bus, or you can say like the domestic bus or grid for that one. So that's why it is known as the miniature version of that grid, so that's why it is known as the microgrid. And now in this lecture we are going to discuss about how those power management concepts are integrating, how that power management schemes are integrating with our normal microgrid applications. And now what we are thinking, that the controllers and everything means basically the controllers we are making it more intelligent, because the adaptable natures of the renewables. Okay, so that intelligent thing is much more suitable for this application. That's why it is known as a intelligent power management scheme for that microgrid applications. Okay, so here we can able to see some of the basic scenario. What are the national action plan taken by the government? So there are different sectors. So we can able to use that how lesser carbon footprint we can able to means we have to minimize the carbon footprint for our conventional equipment. So for that one, government is taking different cares about what are the cares about the generations of the electrical energy. In the you can say like that, in your source point of view, means generation point of view, transmission point of view, as well as utilization point of view. Okay, for the generation point of view, basically we are using conventional fossil fuels for that generation of the electrical energy. Now instead of the conventional fossil fuel, you can able to use some renewable sources. Okay, so that may be the one of the good steps for the generation aspect. For the transmission as well as utilization, most of the cases we can able to see that energy losses. So how optimally you can uses the energy and you can minimize the losses. That may be the another important aspects for that utilizations point of view, means distributed point of view. Okay, you can able to see for that one that the government is focusing different sectors. Okay, so first thing is that conservations of your natural resources like forest, water. Second thing is that we can able to use more sustainable technology for our daily applications or different appliances. We can able to use some sustainable transportations. Okay, so for our common applications, for the transportation purpose, we can able to use some of the LED lamps. Previously we are using some halide lamps, or after the tungsten filament lamp, then fluorescent lamp has came. So more of the cases you can able to see their uses of the energy was more. But nowadays you can able to use some LED lamp which having some 9 watt and it's give you the equal values of your illuminations from the system. Okay, so all over the aspects we can able to use in our daily life. Okay, but problem is that you have to depend upon some of the storage management system, but there are also some issues like that. So after certain time that storage elements, you can say like that battery storage, okay, so it can be cannot be work properly, so you need to change it. So end of the day, the main thing is that what are the different type of waste is generated, okay, from your system or residue of your system, so how you are managing them. So waste management is another good aspect to keep focusing on that. Okay, here we can able to see some of the pollution charts. Suppose in our different cities of our country. Okay, so here we can able to see that pollution is quite more compared to our neighbor countries, different cities of our neighbor countries. Okay, so here we can able to see some of the typical structures of the microgrid. So microgrid is microgrid is the miniature versions of your grid. Okay, or you can say like the local bus of your system, where you can able to connect. It can be connected into different mode. It can be the standalone mode, or you can say like that it can be the grid connected mode. Okay, so that what are the components of the microgrids, you can able to see. There should be some sources, like from this figure you can able to see some of the sources like that. Renewable sources, we can able to see this is your renewable sources. Different types of renewable sources are there. Some of the storage is there. Okay, here you can able to see this is your storage. Okay, so this is your storage, as well as you can able to see some utility grid, means you can able to see that it is your utility grid that connected to your microgrid. If anyhow that any situation occurs, so it cannot be work in standalone mode, so directly it is connected to the grid. Okay, here you can able to see some of the vehicle, okay, that is connected to the microgrid. You can say like that to that your grid. So uh, it is used just like a load, like electric vehicles. Some buildings are there. Okay, so all over the cases you can able to see that most important features of the system is your energy demand. Okay, suppose you have designed a microgrid, so definitely what is the maximum power demand can be there, so you should calculate it. Okay, so and that generations are there, so that sorry, and from the generator, means in this case you can able to utilize like utilize some renewable sources as a generations point of view. And then finally what you need to do, continuously you need to monitor. Okay, you need to monitor. Okay, continuously you need to monitor, then control, and the balance of the microgrid. So monitor means what is your generations and what is your load demand currently. Okay, so if it is generation is more than of your load demand, then there is no problem. So that load will be feed by that standard microgrid, so no problem was there. But if that generation is less than of your load demand, then what happens? So additional power, from where that additional power will come? So it will come from your storage system. So here you can able to see the storage is there. Okay, so storage is there, so additional power will come from the storage. If there is a surplus power in your system, so that additional power also going back to your storage. So that's why this is a bidirectional power flow you can able to see over there. So for the microgrid, so the main thing is that monitoring, then control, how to control it, because you need to balance, or you need to stable the working of your microgrid. If you are not able to do it, so then if we are not able to maintain the stability or balancing of the system, so it can be collapse somehow. That whatever sources we have as well as the storage we have, that is not capable enough to provide you that sufficient to drive your sufficient load of the microgrid. In that case, what you need to do, you have to connect your system to the utility grid. Okay, so that time it can work just like a grid connected mode. Okay, so in our next slide, here we are giving some of the very basic definitions of your electrical grid, microgrid, and smart grid. So all those topics are very well known. So I'm not going to repeat it again. So new thing is that the smart grid. So smart grid, what happened? So in microgrid, you are connecting some of the communications protocol that can work as a smart grid. Okay, so he in this slide we can able to understand what are the different classifications of our microgrids. Okay, so based on that total you can able to understand that they can specify, means based on their mode of operations we can classify. Suppose here we can able to see that based on that mode of operations we can classify the microgrid two types: isolated types or grid connected types. So two types of microgrid we can able to know. Okay, so based on the type of the microgrid, so it is AC microgrid or DC microgrid or hybrid microgrids. Okay, and then what are the types of source of the microgrid? It can be the renewables based or the conventional microgrids, means diesel based as well as hybrid. Hybrid means both renewables and that conventional. Both is integrating with the microgrid. So again, the renewables can be classified into different type. So it can be the solar source fed, it can be the wind, okay, or you can say like that small hydro or pico hydro will be there. Biomass can be there, okay, and the hybrid means all can be connected with the renewables microgrid. And then scenario based means where you can able to study them. So it can be the residential, okay, or industrial or commercial. So all can be possible. Okay, scenario based three types of microgrid you can able to see: residential, industrial, and commercial. Okay, and the rating means load rating. From point of view you can able to classify the microgrid in three types. Okay, so that may be the less than 10 kilowatt, or you can say like the 10 kilowatt to 1 megawatt, and finally that more than 1 megawatt. So in this study, in this lecture, uh, we are going to discuss about only the different types of microgrid. Okay, so what are the different types of microgrid and their discussions? So that questions we are going to deliver over here. Okay, so first we can start with some DC microgrid. Okay, so in DC microgrid, what is the common thing? Common thing is your DC bus. Okay, so whatever sources you are using or whatever loads you are using, okay, whatever storage you are using, so all should be connected to your localized DC bus. So that's why what happens. So you need to design some of that specific converter that can work as an interfacing converter. Okay, suppose you are having a solar photovoltaic. So what is the outcome of the solar photovoltaic? Output of the solar photovoltaic is your DC. So when you want to connect that DC to your local DC or the DC bus of your DC microgrid, then you have to check how much voltage differences are there. Okay, so if that voltage is not matching, then what you need to do, you have to regulate that voltage with connecting your sources, okay, with your sources to the converter. Okay, suppose if we are using that picohydral, or you can say like that biomass, or that solar, or you can say like that wind turbine. So all those cases, what type of output you are getting over there? So that output is your AC output. Okay, so if you integrate your AC output to that DC bus, so what you need to do again? You need to convert that AC to DC. Otherwise, you cannot. Connect them. Okay, so that's why you are connecting that in your AC system. Okay, so AC sources to that DC bus through some AC DC interfacing converter. Okay, so here we can able to see another important factor. So another important thing, it is your solar photovoltaic, it is your wind. Those are working as a renewable sources. So here we are using DC-DC converter, and it is AC-DC interfacing converter. Okay, so here we are also getting some other set of converter, that is your DC-DC converter. This DC-DC converter and this one is a bidirectional converter. Why they are bidirectional converter? So both of the directions power can be flow in this case. So battery and the capacitor. Okay, so battery and capacitor is battery and what type of current? This is the super capacitor or the ultra capacitor is connected with your DC bus through this type of bidirectional converter. Okay, suppose what happens, suppose any suddenly that you know that there is a, you can able to see different loads are connected. It is your output load. So different load is connected over there. So anyhow any changes is there. Okay, in load side directly what happens, it has effect to your system. Okay, so that load means as an electrical engineer, load means we can able to see it's drawing more current. Okay, so if it is drawing more current, that means what happens, the as per the conservation of energy, the power input power and output power is same. Okay, if the load side it is taking more current, so how would you balance that power? So definitely the voltage should be set, means voltage should be reduced to maintain that power level constant. So what happened, the voltage dipping happened, you can able to see the voltage dipping in this DC bus of the DC microgrid. So who will stabilize that voltage dipping? So you are using some of that storage system that can be taken player that can play the key role for maintaining that voltage stability of your DC bus. Okay, so here what type of what type of converter you are using? DC-DC bidirectional converter you are using. So that first it can be connected with the battery, but battery having that, you know, like that electrical disturbances, anything happen, means the time constant is very small. Okay, because that electrical cycle time constant is less. So, but what happened with the battery? The battery response is not so fast of your electrical time constant. So it is in sluggish in nature. So it is taking some time to reach its steady state value. So transient, any changes happen directly or simultaneously. So respond with the battery with simultaneous manner cannot be synchronous. It is taking some time. That's why for the transient domain, who will provide you the additional power? It will come from your supercapacitor or ultra capacitor. That supercapacitor having high power density but less energy density. But in case of battery, it's you can say like that energy density is more than up to power density. So that's why it can take place in the transient response. Sometimes also happen you are having EV in your home, so you are making it charging. Okay, so evening time what happen? Always the demand is high. So that EV if the connected with your system, so you can directly take the power from the EV to your system to run your setup. Okay, so that's why EV also is there. Now you can able to see the AC microgrid. What happened with the AC microgrid? What is the difference between DC microgrid and AC microgrid? AC microgrid, what happened? Whatever source you have, that you are converting all the sources in the DC form. Okay, so suppose if you are having solar photovoltaic output is DC. So again, you are sending then its response to that DC microgrid with passing through some DC-DC converter. Suppose you are having the wind turbine. So if it is DC microgrid, what you need to do? So you can change the, you have to rectify that output of the wind is AC. So you have to rectify that one and feedback to your AC bus. Suppose you are having a storage manager. So storage itself having a taking a DC power. So that's why what happened, what type of converter is required. If it is a AC microgrid, so DC to AC bidirectional converter is required. So sometimes what happen, unnecessary some of the stages you are able to add in this manner. So that's why so sole AC microgrid as well as sole DC microgrid is not been up to the mark. So what you need to do, you have to focus some hybrid microgrid. So what happened with that hybrid microgrid? So whatever sources you have, AC sources you have that is connected to your AC microgrid, whatever DC sources you have that is connected to your DC microgrid through interfacing converter. AC microgrid also have an interfacing converter, DC microgrid also having some interfacing converter. Okay, so both the manner you can integrating with your renewables to your local bus. Okay, so in hybrid microgrid, that's why it is more feasible. So in hybrid microgrid, two buses are there. One is AC buses. One is AC buses. Here you can able to see. Another one is your DC buses. Okay, two the buses are there. So in between of them, so one main converter is there that sending that AC to DC that can convert from AC to DC. Okay, it's an AC to DC converter. Another converter also be there that is also using AC to DC. But what is the difference of this one? So it's an interlinking converter, means it's a bi-directional inverter. It is well known like that, bi-directional inverter. Suppose you are having a AC bus and DC bus. So anyhow, any of the bus having more loaded condition. So from where additional power will come? So additional power normally will come from another converter, or you can another bus. Okay, so by that manner you can able to maintain the stability. So this work actually basically we are focusing about some power electronics converters. Okay, some after some power electronics converter we are giving focus about some other working. Okay, so how the power management techniques implemented, how it is we using for our practical applications. Now we can able to focus on some of that interfacing module. Okay, so what are the different types of power electronics converters are using for this application? So first we are getting that first one is that your interfacing converter that can interface your renewable sources to your microgrid. So it's your interfacing converter. Second thing is that you can able to see that bidirectional converter. Suppose your storage is directly connected with your microgrid. So to whom it should be connected? So there should be have some storage. Okay, so by the connections of the storage you are having some specific converters. Okay, so storage is important. So bidirectional one. Okay, and you can say like that finally means so interfacing converter, bidirectional converters. Okay, so sometimes you can able to focus on power quality issues. So all those things are important. Okay, for a interfacing module. Now when you are designing some of the converters, so that should maintain some of the international protocol. So who is deciding this protocol? Basically IEEE having some standard. When we are designing the converter in your laboratory, after that what happened, we should test all the specifications. Okay, so whatever standard has given to us, so that should be specified. Whatever results you have received from your setup. So both the way we can cross verify and we can able to understand. So if that protocol, suppose THD maximum 5% is tolerable, so that protocol should be such a way, so you have fabricated the thing such a way, should not be that beyond that standard protocols are given by the IEEE. So here we can able to see some of the primary protocols and some of the protocols and the standards are given there. Now when you are going to design some of the converters, so you have to maintain some important steps. Okay, first like that whatever converters we are using, that also having some non-linearity. What type of non-linearity is it? Is a switching non-linearity, means the converter either switch on, either switch off. Okay, so that's why the non-linearity is there, that is called the switching non-linearity. Now based on the requirement, so you should select the topology of the based on the requirement, you should select the topology of the converter. I mean, suppose we can take some example. Okay, so we are having a DC bus. Okay, we are having a DC bus. So one battery also connected to the DC bus. Okay, so now the DC bus temperature, DC bus voltage is 48 volt. Okay, and whatever source you have. Okay, suppose you are connecting that DC bus with a battery bank. The battery bank output is coming 12 volt. Okay, so that cannot not directly connected through this manner. So what happens? You have to first select the topology of the power electronics converter. So for that, what topology is required? So it is step down of voltage. So step down converter is required for these applications. Okay, so step up converter as well as step down converter, both is used for these applications. Basically when that additional power will come from your additional power will suppose you are having a battery power, so battery power is come from your converter to your DC bus, then 12 volt to 48 volt stepping up is required. So what type of converter you should design? So it should be the boost converter. Okay, so reverse thing happens. So if you are having a 4 power bank, but their temperature is quite high compared to your sorry, its voltage is quite high compared to your. So from where you will get it, so additional voltage will come back to your storage. So both the way, so that that's why it is known as the bidirectional converter. It can work both the directions. But what happened that as you are using switching devices, so all are having the switching nonlinear. So you need to design that modeling in such a manner so able to you can able to reduce the nonlinearity. Okay. So and finally, what happens? So after getting that equation, that after getting all those things, if you could see in the form of equation, you can able to understand that all are happening in the mathematical modes. Means suppose if you are able to implement it, so how you are going to implement? So you have to design the control circuit, and the control circuit will fade you. Control circuit is from the control circuit you will get some control signal. Okay, so after that you can able to control it. Otherwise you cannot. Okay, and finally we can go for the implementation. So implementation can be done in different aspects. So first we can do the implementation in computational, then experimental. Okay. So and if the converter is working fine, so how do you know? Okay. So first thing is that you should go for that good line and load regulations. Okay. If it is okay with those things, so converter can be working any other disturbance suddenly if the source is not there. So that's why we are doing the load studies. No? So basically how it will be behaving or responding when that electricity is not there. So that's why that controls, so regulations is there. Okay, then we are taking care about the transient system. So we have already discussed in this matter. So the system having less sorry, transient stability. So system battery having that less energy, less power density, and capacitor having more power density. So for the transient purpose, you can able to see some of the results. So it look like a spike kind of thing. Means that durations that super capacity is providing. After some time, automatically the storage has open. At that time, it will not work. So that communications and all those things are very much important. Okay, so first topology selection. From the topology selection, you can able to anybody can able to fix up the maximum how much cost can be there. So they just go for cost settling also. Okay, so mathematical is important for design the controllers. Okay, so LTI means linear time invariant system. You should design for mathematical modeling of your controller. Okay, so mathematical modeling of your converter. After that, you can able to design that mathematical expressions of your controller. Okay. So here some steps are there to find out the linear equations of your converter. So first step, what step we are doing? So we are doing that on state differential equations, on state equations as well as off state equation. After that, what happened? After getting both of the equations, we are doing that state phase average modeling. Okay, so where we will be able to reduce that some of the ripple component. If you make it zoom, so we can able to understand that some ripple components are there, so it can be minimized. Okay, so third point is the AC perturbations as well as separation of the AC and DC. So definitely, so now we can separate that one DC component and that one AC component. Okay, after that, what you need to do? You have to go for that control to output plant transfer functions. Okay, so here we are able to understand that both the power conservation and power restraints means P input equals to P output. Okay, so if suddenly load is increased, means then what happened? P0 will be increased. Okay, when a load side current will be increased. So maintaining the flux constant. So what happened? Sorry, maintaining that a constant. So uh, so what you need to do? So first you need to sense that output voltage, then you have to compare that output with your reference signal. After comparing with the reference signal, then some error signal will be developed, and that error signal should be passing through the compensator circuit, and finally we will get that work. Okay, so after that it can be work. Okay, this is the very you can say the very basic block diagram of that one. Okay, suddenly that output voltage is dipping, so additional power will come from this side. So you can able to compare with your reference, so definitely reference value is high. Okay, so that definitely will be coming, that definitely will be considered for the calculations. Now other different type of interfacing converters we can able to see as well as their characteristics. Okay, so we are using that as a MPPT algorithm. Okay, so MPPT is using for this purpose. So whatever, so photovoltaic or solar photovoltaic you have to implement it for extracting the maximum power. After that, you have to calculate that what is that PMM, okay, and how the relation with the duty ratios, that are the very important thing. Okay. Now we are using that SSM, state phase average modeling, for the boost converter. Same process we are following like your same process we are following like your you can say like that, it's a boost converter. Okay, so here you can able to see that both the sorry, here you can able to see both set of sorry, here you can able to see that both KVL and KCL methodology for find out some of the unknown. After that, what we will do? After that, we can do for the fabrication part. Okay, so for fabrication work, so for this one, we can able to understand. Okay, so first we have to write the set of equation KVL and KCL. Then we'll do that. Then after that, we'll do some. Hello. Yes. Okay, so here we can able to see that different set of equations. Okay, so then averaging we are doing, so duty weighted averaging. Okay, so here you can able to see that duty weighted averaging. Okay, so after that what we will do, then we will do the perturbations. Okay, then we are having some plant transfer function directly we are having, so directly we can place the value and we will get that output to control to output transfer functions. Okay, so here we can able to see that one RHP0 is present in that boost converter. Okay, so that can be possible due to the constructions on that converter. So there is some effect on that that will come. So for the buck boost converter also happened the same thing. We are having two set of equations like KVL and KCL. Okay, so from that on state equation and off state equation, both the mode of operations, we are having the equations, and after that what we will do, we are again do the averaging techniques, implementing the averaging techniques or duty weighted technique. Finally, we are separating that AC component and the DC component, and AC component will get the steady state value, and from the AC component what happened, and we from the AC component we can able to evaluate. So we can able to use by using the Laplace transformations. Okay, so here also the same thing. So from set of equations we have able to find out finally that state equations are getting with the plant transfer function, and after replacing the value we will have that one as a plant transfer function. So in this plant transfer function also having that a non-minimum phase problem, that means on pole at 1 0 one right hand plane 0 is there. Okay, so if it is there, so from the basic construction gain margin there is not so much changes, but what happened in the phase margin there is a drastic changes. Because of that, initially there are the drastic changes are there, because there you can able to see that sorry. So here we have to design some the special type of controller that is called the type controller. So type controller can be categorized three types: type 1, type 2, and type 3. Type 1 controller, it's look like a one pole at origin, and it's a one constant is there, means proportional constant, you can say like that. Okay, so but problem is that in type 1, so its response is not good, its response is quite slow. So that's why one lead controller can be introduced with the type 1. So directly he lead control sorry type sorry one controller directly used with your converter. So what happened, so it can work better. So a non-minimum phase problem means you can select the maximum phase delay system. Suppose you are having a second order system, so the two poles are there, so that two poles can combinedly giving you minus 360. If one right of plane 0 is there, so that also can provide you another negative, another additional phase lagging over there. So that's why what happens. So you have to use some type 2 and type 3 compensator. So type 2 compensator, two poles at origin, one pole at origin and one pole and 0 is cascaded with just like a, you can say like that. They are cascaded with the controller. Okay, and type 3 compensator, similar kind of thing, but its calculation is quite different, but the response is very fast. So in this case what happened, in so they are connecting the directly. Okay, so type 3 controller, type 1 controller is a integral controller, type 2 controller is a integral cascaded with some lead controller, and type 3 controller is, you can say like that, lead compensator. Okay, so here we are having some of the setup like that. We are designing that tri-state boost converter. So in this tri-state boost converter, what happens? So you know, if you will to see the RHP problem, so RHP problem cannot be mitigated directly from the topological aspects as well as control aspects. So from the topological aspect, how you are nullifying the RFO, that you can able to understand by using the tri-state boost converter. What with the tri-state boost converter? That converter having one additional switch that can bypassing, or you can say like the draining out the inductor stored energy of the inductor. So that's why it is not coming. So the non-minimum phase can be modified or neglected by using this method. So here we can able to see some of the waveforms of here we can able to see that different waveforms for type 3 compensator. First waveform is directly for that uh, first waveform is the coil voltage. Okay, means if you are using that coil, okay, so inductor coil, so that across the inductor how the voltage can be developed. Second one you can able to see for the gate pulse for the main switch, and last one is your gate pulse for the auxiliary switch, and middle of them are the, you can say like the current pattern. Okay, so these all are the very basics of the tri-state boost converter. In this case, there is no non-linear phase problem in the right hand side. Internally boost converter also means two boost converter connected in two boost converter can be connected is an integrated factors. Means both can be work together, or if based on the code you have given, so they can work. Okay, so what will happen with the internally boost converter? Internally boost converter response is very fast. Okay, time constant is very low, so response is very fast. But it will take some time. Okay, so means internally means you can select that the input ripple can be minimized. Here you can able to see that single phase. If that one is single phase, inductor current is how much ripple? Huge ripple. Here also single phase is having huge ripple. So if both the, here we have considered two converters, so both the converters are connected, so you will get some lesser ripple. Okay, and you can easily get the very fast response. So the transient response you can see in this diagram. So now what we are doing, so tri-state internally boost converter. The first time we have introduced the tri-state internally boost converter. So internally boost converter having non-minimum phase problem, but its response is very fast. A tri-state boost converter response is sluggish, but it having some work uh, on this domain. So that's why that internally boost converter is well accepted. Okay, so in this case, what happened? We have plotted, and some of the means some of the graph is plotted, some of not plotted, but in this way, so you can able to see that both the property can be persist, and they can uh, and both the properties can be persist, and it can be done in very better manner. Okay, because the response is. Okay, now we are talking about that AI. Okay, so now intelligent control. So AI implementations for the power management in Microgrid. So there are different aspects for that AI implementation. So first thing is that forecasting, means weather forecasting. Okay, energy generation forecasting, land for load balancing. Okay, so predictive maintenance. So these all are the AI data. Why AI you are using? Because the most of the things are very uninterrupted. So being uninterrupted. So most of the things are interrupted. So what you can do, so based on that you can able to applicable different intelligent controller for it. So automatically it can be behave. Because of that, storage is not good some of the times. Okay, means whatever generations are there, so it cannot be stored all the time. So surplus power, where it will go to the converter, through intelligent converter it will go to your any of the. Okay, so other thing is that predictive maintenance. Okay, so energy storage management all should be there for the AI application. So predictions for the AI applications, first thing is that you have to arrange the you have to arrange some data. So from the data you can train your system. Then you will give that system the some of the assignments. Okay, so that should be. Now that different algorithms are also using for the power management of the microgrid. So first thing is the reinforcement planning, RL method, predictive analysis, fuzzy logic control, generic algorithm, parallel sorry generic algorithm, that particle sum optimization, neural networks, okay, model predictive control, game theories, and then swarm intelligence. These all aspects you can able to get it, and it is used for your intelligent control design. So here you can able to see some ANFIS based concept. So in ANFIS based concept you can able to see that Z. Okay, so Z is a function of X and Y. Okay, in the middle there is a different layers are there, W layer, W1 Z layer, mod of W1 and ZI layer. So based on that you have to select which one. So basically here ANFIS is using, okay, for getting. So some fuzzy based MPBT algorithm have implemented, and some waveform you can able to understand. Okay, so I hope you people are able to understand whatever I am telling. So end of the day you have to maintain that DC volt fixed. Here that DC volt you should make it fixed. Okay. Now we are talking about bidirectional converter. Just for a minute. I have already told you that bidirectional power flow can be done from your battery bank to the DC link voltage, as well as DC link voltage to battery bank. So sometimes it is drained to the boost mode. Suppose battery voltage is 12 volt and DC link voltage is 48 volt. So battery is want to discharge from 12 volt to 48 volt. So what type of converters are needed? So definitely it should be the boost converter. Okay, so again same different reverse thing happens. So battery bus voltage is 48 volt and battery voltage is 12 volt. So if the in evening time battery has discharged, so now you need to go for the charging of the battery. So definitely that reverse thing happen. Okay, so both you can able to connect both that one. So boost and back, both the mode if you connect there. So the switches you can able to use, that should be the bidirectional switch, and it is connected anti-parallel. Here you can able to see that individual switches are there for the bidirectional. You can connect it. Okay, so and that power can be transformed from battery to DC link voltage or DC link voltage to battery. This is a hub structure. Okay, so what is the hybrid type of converter? Hybrid converter, both AC and DC can be possible. So based on what topology we are using and how we are selecting the topology, working on that will be important in the hybrid converters. Now we are having some example. Okay, so we are having some 3 example with MATLAB. Okay, where we are going to discuss with some applications, means results, how that power management process can be done and what are the different type of controller you are able to use. So here first thing is that on DC converter is required, that converter is fed to the MPPT controller. So if your solar photovoltaic connected to your converter, so how that converter will work? So by through that MPPT controller. So for getting the MPPT and implementing the MPPT, so you have to change the battery voltage, sorry, panel voltage and current Okay, so based on that, you can able to design the duty cycle, and that duty feed to that DCC converter, and it can be work. And finally, you are trying to maintain that DC link voltage making constant, but it is not properly work. But here you can able to see that DC bus is there, DC bus controllers are there, so that directly connected to the bus of the system, so it can be so energy can be transmitted better manner. Okay, so both the voltage mode control and current mode control, both the mode of controls you can able to use for these applications. Here there is a three diagrams. First diagram you can able to see that irradiance has changed. Okay, here you can change the solar irradiance by without changing that changing the irradiance without changing the voltage controller. Okay, another diagrams are there, so you have changed everything with changes of the with voltage controller. Okay, so then what happens, so here you can able to see the output also. Okay, so output is not output you have received. Okay, so output you have get it. So here red color one is that controlled one, that's why there is no disturbance, but here the green color is not been in concentrate, so that's why what happened, it is affected. Okay, now four conditions we are observing for a half bridge converter. So first voltage loop is there. After the voltage loop, the current control loop is there. Then it can feedback to that. Then it can be feedback to your converters. Okay, so now again it's a converter. So what will be the problem? So it's a non-minimum. Sorry, not non-minimum. It's an switching switching nonlinearities are there, on off nonlinearities are there. So that's why we have designed a state phase average method for uh, getting your transfer functions. Okay, then finally you tune it in the uh, sorry, there is a CISO tool. Okay, MATLAB CISO tool is there, you are able to tune it over there. Okay, so here different types of values are sorry, if the battery is charging, so SOC level is increasing. If battery is discharging, so it is also decreasing. So there are two types of controllers, so KP and KI. So both the converter having two set of equations. Okay, so here we can able to implement it. First condition, generation and load both are in same. Okay, in that same condition, what happen, any changes in the generation, same changes you can able to see the load voltage. But what about the load current? As you know, there is a conservation of the power. So if you want to maintain the conservation of power, so what happens, that additional power should come to store in that storage. So you should use some of the converter that can use for the storage purpose. Okay, so if they both are same, so both so both are same means, so whatever generation is there, power also increasing. Now the case, it is working as a back mode, means whatever source you have. Okay, so few sources they have not given. When it's suppose solar photovoltaic is there, the generation is more than of your deliverable, as simple as it. So what? So additional, so main thing is that you have to provide the additional power from the battery. So here you can able to see the battery. So battery current is negative initially. Power is negative means current is negative. So current is negative means battery is drawing more current. Okay, so battery, if battery is drawing more current, so definitely the voltage sagging is there. So for reducing the sagging, so we need to connect the converter. This is a back mode operation. So initially what happens? So back mode operation means battery voltage is more than of your gate voltage. So battery is discharged. Okay. So if battery is discharging, that means the current is positive. If current is positive, so there is a chances for the energy stored. So, and that way it is the SOC level is increasing. Conditions we are having that mode 3. So in this mode, the PPV less than P load. So P battery equal to P load minus PPV. So from where additional power will come? Additional power will come from the battery. Previous case, additional power will be sent back to the battery. Okay. In this case, additional power is coming to the battery. These are the very basic idea about that different islanded conditions of your different islanded conditions and their okay, this is a boost mode. So now both are changing. Current is also increasing, and other things are also changing. Currents are increasing, so that's why battery current is negative first case. Then it will be positive. So everything can be done over there. And finally you can able to see its certificates of both SOC level. Okay, so increasing and decreasing. Okay, so at that point what happened, you are changing the solar irradiance. Okay, so solar sorry, battery current is suddenly changes, so that's why battery is discharging, so the SOC level is discharged. Okay, here you can able to see the DC creative voltage. Okay, now DC bias voltage, and that is maintained constant. Okay, some experimental diagram of a bidirectional circuit converter. Okay, now we are giving more trust on that hybrid microgrid. So hybrid microgrid, what we have told, so whatever sources you have, you are connecting with one grid, another grid also be there, another it can be connected with another microgrid, or it can be connected with your components. Okay, all those things are important. So here you can able to see some different types of renewable sources, solar photovoltaics, then wind, then you can say like that battery also be there. So what you need to do, you have to connect the solar capacitor inside of that one. That example we can able to understand that where boost converter is there. Okay, then bidirectional half bridge bidirectional converter also be there. You see sorry, here you can able to see like that solar photovoltaic, you can able to see the solar photovoltaic is there, so irradiance and temperature is there. After that here is a converter, boost converter. Then you can able to see the load. Before the load, that another storage, sorry, solar photovoltaic is connected, means we are combining them and directly give it to the uh, load. Okay, so now it can be drive the load, and finally what happened, you can able to see two sorry, there is a half bridge converter. That half bridge converter, you will provide the gate pulse of the half bridge converter. By that way it can be managing the power, means whatever coding you will write, that should be there inside of the microcontroller board. You just dump it to the computer and it can be sorry, it can be worked. So small signal analysis we did it for getting that uh, controller parameters and all those things. Now we are having 6 stages, 6 cases. Okay, 6 cases are there. So from that cases we are able to see their changes of your load demand and other cases. Okay, how the power management can be done. So first case is what happened, you can change the load demand. So load demand is suddenly high, so power is increasing. So if the power is increasing, so definitely power is a component, positive component. So from where we will get that, because the voltage is less in na, so from where we will get it. So you can able to that additional power is coming from your battery. Okay, and you can able to see over there, there is no changes in that wind power. Okay, there is no changes in that wind power. Battery power can be changed because the additional power will come from the battery. And another thing is that that you are not changing the other parameter. So other parameters values are fixed only, fixed on this specific parameter. This is for the case 1. In case 2, the what happened, that variable solar irradiance with constant load power. Now load power is constant, so irradiance has changed. Okay, so if irradiance is changing, so definitely we should get some. If we sorry, we will get that wave. Okay, means if you want to change that capacitor. Okay, so definitely it can also be possible. So here, what we have observed that. P load is constant. Okay, P load is constant. Only P PV is moving. P battery and P moving. If both are moving, so we will get that one. Okay, so you will get that steady value of the DC. Here you will get the steady value of DC. But problem is that in this steady for DC, but some of the fluctuations are there that can also be minimized. So in this case, first some chargings are there and dischargings also be there, increasing and decreasing. Finally, in case 3, the temperature is changing or variable that and that constant load variation. So here you can able to see the changes here. So here you can able to see some of that battery current. Okay, here it is your temperature frame. Yeah, okay, so solar irradiance also changing. Okay, solar irradiance also changing. Okay, and based on the changing of the solar irradiance, you can able to see that voltage is maintaining constant. Case number 4. So you can able to see that vary that wind speed. So if you vary the wind speed, so from where additional power will come? So this is wind speed. Okay, so additional power will come from here. Uh, of your DC bus, so who will take care about it? The DC bus converter will take care about it. Okay, so it is your time constant different. Okay, a VDC, and finally you will say like that how the SOC level has changes. Okay, and finally last one, that variable speed, solar irradiance, solar temperature, but constant load power. But all the process can be done. You can able to see some of the irregularities, means some of the notchy diagram you can able to see over there. Okay. Now all those things have changed. Power, previous cases power was constant, rest of the power all are changes. Now so everything has changes. Wind speed, solar irradiance, solar temperature, load power, everything has changes. So battery is playing a key role for maintaining all those things. Okay. Then we are having different schemes of power management. Okay. So hybrid storage management we are using for maintaining the SOC value. Battery and SOC units will be employed together in that process of hybrid energy storage systems. Okay, supercapacitor have high power density by the lower energy density. Battery has the vice versa, in reverse. The batteries have lesser density, and battery and supercapacitor energy storage units are together. So here we are using some fuzzy logic based compensator. Okay, so that can be used, that is used for that simulation work. Okay, so a lot of sources are there, then different lot of sources are there, then algorithms are there, how it can be how it can be work. Okay, like fuzzy based controller. So finally we'll do that variable load. Okay, different conditions we able to see. So initially you can able to see some spike. Okay, that spikes are there, same condition, load is increasing. Okay, so spikes are there. So why that spike? Basically the meaning of the spike is that meaning of the spike is that transient response, it is working fine. Okay, so load is varying with the DC microgrid, but it is working very fine. And SOC level, how it is charging, it is showing over there. Okay, so SOC level, and then conventional PWA. So if you compare them, you will get this one. Okay, some tables are there for better understanding. Now variable generations with the DC microwave. So you can able to see that is already there, the transient, that super capacitor already there. So now we are increasing the variable generations. Okay, so if you generate, if you will to do that variable generations, so you can able to plot that SOC level, how it has changed. Definitely it is changing. Okay, so now variable load with the hybrid microwave. Okay, so in this case, what happened? In this case, what happened? There is a supercapacitor definitely for implementing it, or you can say like that. You can able to compare that proposed one with some conventional one also. Robustness study or stochastic analysis, parametric uncertainty. So you are providing the disturbance in the, and you can able to understand how better manner it is tracking and all those performance. So these are the some features of our setup we can able to develop here, and we are using on it right now. Okay. So there are different types of controllers. Controller means we are talking about synchronization. Synchronizations can be done in primary side as well as secondary side. So sophisticated controller is also important. In that regards, there are three types of controllers. One is the decentralized controller, centralized controller, and the distributed controller. So decentralized controller have an individual converter and that equipment having some individual controllers. Okay, then what is the problem? So there is no coordination between in two of the controllers. That is quite challenging. Okay, so that's why concept has changed now. Now it is your centralized control. But what is the problem in centralized control? Centralized problem in your circuit is quite complicated. So anyhow, any fault occurs, for getting the fault is quite difficult. Any damage that happens, so entire the thing has been replaced. So some problem is there with that centralized control. So only option is the decentralized control, or sorry, distributed control. In this case, there is a good coordination between all aspects of that, all the sorry, the distributed controller for both of the institutes. Okay, so this is well known and good for applications. Among of them, there is other controller also with there, suppose group control, communication based control. Now, a lot of works are going on that. Um, Inverter controls and oscillatory controls. So these all are the different applications. Okay, and that lots of works also going on in the coordination control. Okay, so these all are the very important idea for that application purpose. Okay, so thank you. If you are having any doubt, any query, please let me know so I can also discuss on that.
Participants, if any questions, please ask.
Any queries from your end? Okay.
I think there is no queries from participant side. So thank you very much, Professor Arnab Ghosh, for your informative session on power management. And tomorrow we'll start our session at 10 a.m. Thank you,
Okay.
everyone. Have a good day.
Thank you. Thank you.